Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Well, good morning, everybody. Thanks for coming. Today, it's my great pleasure to introduce Aditya Akela to tell us about some of the recent work he's been doing on OpenNF. Aditya, for those of you who don't know, is on faculty at University of Wisconsin and has done a lot of good work since he's gotten there in redundancy elimination, complexity, understanding quality of experience and whatnot, and a lot of his work has been really influential. Personally, I think I've known Aditya now for 10, 15 years. I think we started grad school at roughly the same time, doing overlapping things to both our miseries. But, you know, we grew up. Anyway, without further ado, I'll hand it to him.
Thank you. Thanks, everyone, for coming to this talk. So I'm going to be describing this system called OpenNF that we've been working on for nearly a year now. It's basically something that combines the power of SDN with software virtual appliances, and it enables a variety of distributed middle box style applications. A lot of this work was led by my student Aaron Gember, but he got a lot of help from Rajay, who's in the audience today, and from Junaid and Robert as well. So how many of you here are sort of know what middle boxes are and SDN is and so on? Who doesn't know, I guess? Is there anyone who needs some? You don't? Okay. Really? Okay. All right. So
Right, you have some slides for it.
I do, but okay. So let me just quickly walk through them. All right. So I'll just start by telling you what these software virtual appliances are and SDN and why they're being used, and then I'll present the motivation for the distributed processing that we are doing. So traditionally, you build your networks out of routers and switches, and they provide very basic functions like connectivity between different points, simple access controls, and so on. But often network operators want more packet processing functions from their networks for security, for performance reasons, and so on. So network functions or middle boxes, both of these are fancy terms. I don't know what they exactly describe, but they are terms, are devices that help fill this gap. So they allow an operator to introduce custom packet processing functions into their networks. And these are a lot of examples out there, things like load balancers for balancing, in-network load balancers for balancing load across servers, things like firewalls, SSL gateways, intrusion detection prevention and detection systems, traffic scrubbers for security, caching proxies, and WAN optimizers for performance, and so on. In contrast with their routing and switching counterparts, these devices maintain, they are stateful in nature. They maintain a lot of state for the flows that they process. So that's a big difference between these and routers and switches. So you may be wondering, why am I working on these things? These are not arcane. They're actually very popular. A recent study from Justine Cherrier and others found that these middle boxes are quite widely deployed across a bunch of enterprises out there. This is an average across 55 different enterprises, and the key takeaway from this graph is that there are at least as many of these appliances deployed in enterprise networks today as there are routers and switches. And this is not just true for enterprises. Other networks such as ISP networks, cellular networks have a similarly widespread deployment of these devices. So it's not a surprising thing that the market for these devices is a rapidly growing multi-billion-dollar market. And more as newer applications arise, newer devices arise, newer threats emerge, new appliances are designed, and they get deployed. They're popular, but they're also extremely painful to manage. In general, large networks are hard to manage, and once you throw in these custom packet processing things, they require custom configuration, custom wiring, and a lot. They're generally difficult to reason about, so they are pain to manage. So this is sort of where software appliances and SDN come in, and these are two trends that are actually making the management of these networks that have these network functions simpler to manage. So the first trend is that traditionally these were hardware devices. They're moving into software. This is Riverbed's Steelhead appliances is its virtual counterpart. That's F5's load balancer. This is an in-cloud counterpart of that. These software alternatives are cheaper. They're easier to deploy, upgrade, customize for a particular network, and so on. So they kind of bring down the management burden significantly already.
The movement is actually hardware to software, or the movement is from customized hardware to commodity hardware? Like,
yeah. So these are. So it's a mix of both. So I think there are models where you would deploy on a commodity hardware, sort of an extensible middle box, along the lines of CoMB, where you can deploy a bunch of different middle box applications, and they would all be running in software. But these are sort of machine images. These are sort of packaged as VMs that you could deploy inside EC2, for example. So both of those are fairly popular trends. Yeah.
Management overhead really less.
These things become easier. So it's hard to quantify exactly, whether things become simpler. Just hold on to a little bit. I think once we talk about SDN, some of those things will become cleaner.
My question is more towards the capacity standpoint, right? Essentially, it's replacing one big iron box there, but replacing tons of smaller, lightweight processors. The ratio is not 1-to-1. Your slide essentially showing.
Oh yeah, it's not. You need to use multiple of these. I agree with.
Management costs increase substantially.
Yes and no. I mean, let's wait up to the next slide, and then we can revisit this question. Okay. So the second trend is the use of SDN. Again, most people hopefully here know what SDNs are. SDN is basically a framework that provides you logically central control over the forwarding state of a network. And to see how this is improving management of networks with these NFs or middle boxes, note that traditionally the way to use these devices was to deploy them in choke points within the physical topology, and then wrestle with distributed routing protocols to funnel traffic through those choke points to get some traffic subsets processed by them. With SDN, because you have sort of this control over state, you can deploy these boxes off path and then punt traffic in and out of them to specific traffic subsets in and out of them. And that immediately takes away the central points of failure and attack here, and central points of network congestion. And sort of that aspect of the management story kind of becomes better. The other thing you can do, which is sort of an interesting line of research in middle boxes, is that you don't need, what you could do is you could have multiple different kinds of these middle boxes hanging off of the network, and you can chain traffic through those different sets of middle boxes such that specific traffic subsets traverse specific subchains, and that allows you to realize a variety of interesting, rich, high-level policies. And that kind of stuff is something difficult to realize with hardware appliances deployed at choke points. Okay. So what this talk is about is sort of building on this notion of decoupling of middle boxes from network topology that SDN enables. What this decoupling means is that you don't need to use one instance of a middle box. You can have multiple instances deployed at different locations within your network, and you could use SDN as a way of steering traffic subsets towards those different instances. But SDN actually gives you more teeth than that. It allows you to dynamically reallocate traffic across instances in order to achieve sort of dynamic control over the distributed processing happening across those instances. And you can use that to realize various high-level properties. So one of the things you could do, for example, you could immediately make load balancing more effective. So for example, you can, in this case, whenever some middle box runs hot, you can immediately move load off of that middle box by dynamically reallocating processing for those flows across to a different middle box. And this allows you to extract maximal performance across these different versions of the middle box at a given cost. So this is sort of what I mean by the software appliances together with SDN kind of making the management story simpler. Right? So there is some element of CapEx and not having to worry about doing many of these things manually. I don't have a concrete argument that this actually makes management simpler, but
I think it makes it harder.
why is that?
For some scenarios. For example, think in terms of this standard. Nikolai is here, he can vouch for maintaining the software state across multiple instances, ensuring you keep on rolling updates, ensuring you have a global view of correctness for the whole system, right? So think of what you could do just on one box. Now essentially you have to do on roughly, ratio from 1 to 100 to 1 to 1000. Right? So replacing a single F5 load balancer, you actually need at least order of hundreds of software VMs to actually provide that kind of capabilities. So the management actually costs quite increasing. Essentially becomes much more painful because of in terms of ticking time bombs that one of them goes out, then a subset of your customers are not able to reach their applications. Right? Even in this kind of a figure,
Yeah.
they are stateful, right? So essentially, whenever you're making any kind of a change, you have to transfer the state.
Yeah.
So what happens to connections which were actually
Okay, I think you're making the case for OpenNF. So let me actually, again, maybe this is not the place I should have stopped. Okay, so I think we are in agreement. So, there are some aspects of this that become simpler. You don't have to put these in the middle of the network. That's also the reason why, for example, SLB is used as opposed to a big honking F5 load balancer today. It gives you much greater capacity, without having to babysit custom hardware, right? But anyway, that's kind of the trend today. Things are kind of moving into hardware. But what I wanted to get into is it's not just sort of simple load balancing. It actually the ability to do dynamic reallocation of distributed processing allows you to build novel abstractions. Okay, and so one example is in the abstraction of a infinite capacity middle box, where if a middle box instance runs hot, you deploy additional copies of that instance, and you distribute subsets of traffic across those copies. Even a richer abstraction that you can provide is that of an always updated, always available middle box, where suppose you want to update this middle box with some security patch, you deploy a hot standby that has this patch. Once this is ready, and that will be clear in a minute, in a few slides, you take down this middle box, use SDN to steer traffic to this updated middle box, and then you have an always updated middle box abstraction. You can do something even more powerful. You can dynamically enhance the functionality of a middle box by leveraging an in-cloud brawnier version of this middle box. So for example, if this middle box is seeing something anomalous for a certain subset of traffic, you can take the ongoing processing for that specific traffic subset, hand it off to a brawnier version in the cloud for additional processing. Okay, so with sort of if you had the ability to do this kind of tight control over distributed processing, then you can realize all of these interesting rich abstractions. So a lot of cool fun things can happen if you can get middle boxes and SDN to play with each other. This may not be funny now, but hopefully it will become funnier in a couple of other slides when I'll bring back these two characters. Okay, so what OpenNF is, it's a control plane that can support key semantics in these distributed processing applications, specifically for all the dynamic reallocation actions. Going back to the comment that you made, the kind of guarantees that it can make is to ensure that the reallocation actions can be safe, and that this reallocation can be done at any particular point in time. So by safe, I'm talking about something like a safety property, which is output equivalence, so such that when you reallocate traffic, either to respond to load or whatever else, you can reason about the fact that the outcome of the actions after reallocation is similar to that of one single middle box with equivalent infinite capacity. And this is sort of a liveness property, and what this essentially means is that an operator should be able to trigger these reallocation operations at any given point in time, and he should be able to argue that it will finish sufficiently soon, within some bounded amount of time. Okay? So there is no control plane out there that does this today. We are the only system that can provide these guarantees. Some of you know our SIGCOMM reviews are out for rebuttal, so this is just my way of making myself feel good. So it's, you can kind of every day I look at myself in the mirror and say, you're my hero. No matter what the reviewers say, you're doing good work. Okay, but more seriously though, this is actually the first system that can provide these kinds of guarantees. So having these kinds of guarantees are useful for two reasons. The first thing is that it is actually a necessary basis for some of the new abstractions I described on the previous slide. Without having these kinds of guarantees, it's hard to build a dynamic remote enhancement kind of middle box. And it also forms the basis for strong SLAs, that you can actually reallocate load without taking down the middle box or impacting availability, or that you can respond to load within some small amount of time, like within a few milliseconds. Okay. Just to reinforce that further, you can offer strong SLAs in these things like load balancing, elastic scaling, and the always updated middle box kind of applications I described on the previous slide. In the case of load balancing, for example, you can ensure that the load reallocation mechanisms are sufficiently responsive and they don't impact the quality of the decisions made by the NFs in question, or the middle boxes in question. And in terms of these kinds of guarantees being necessary for being the basis of new abstractions, without being able to reason about safety and liveness, you won't be able to build this dynamic invocation kind of application that I was describing. You fundamentally need the ability to be able to move flows and be able to argue that that operation has these safety and liveness properties. Okay, so OpenNF is a system that can provide these guarantees. So, yeah.
What is the real need for those guarantees? Like, why are you taking such a strong stance on, like, in the end, I think the basic abstraction of the network itself is, packets can be corrupted, packets can be dropped, can be duplicated. So why go for such strong guarantees?
So typically when packets are dropped or reordered by the network, the middle box has some logic to deal with that. Okay. And the outcomes are sort of basically a function of those possible inputs, right? What we are saying is that we want to be able to support reallocation actions, and we want to make sure that the reallocation doesn't introduce other unexpected inputs that the middle box did not take care of. So we want output equivalence with respect to whatever the middle box's internal logic would do for just network induced losses and corruptions. Does that make sense?
Yeah, so I was thinking, like, I guess if you're willing to, like, admit, let's say, duplication and drops in the network, then it seems like the allocation stuff, reallocation becomes trivial maybe. You basically you bring up another middle box without actually worrying about any kind of consistency, and this middle box has logic to deal with duplication and drops, and why is that not enough?
So I'll come to an example where that is not possible. So basically, for example, an off-path IDS, if the network doesn't induce any drops, then anything where there is a missing event, that would actually trigger some sort of an alarm for the off-path IDS. Or if some kind of reordering happens, it would trigger an alarm for the off-path IDS. But in the case of an off-path IDS, it doesn't have the ability to request those dropped packets, because the application may not retransmit that. So it would have to deal with that missing hole in some specific way. What we want to make sure is that the reallocation does not change the nature of the decision that the IDS makes, given what is happening with the application and given what is happening with the network. Does that make sense? So if you can engineer a network that that does not corrupt packets, and that does not introduce reordering or drops, then the middle box's output should be the same with or without reallocation.
So if we have a network that is not doing it, but the fact is we do have networks that corrupt packets and drop and duplicate. So what that means is, like, maybe it's going back to end-to-end, like the middle box logic should be robust enough to these things, in which case you don't need like this, a control plane with such strong guarantees?
Yeah, so I think, so let me get to the loss freeness guarantee, and there with that example we can revisit this question, right? So I think in that specific case, we will see how we are sort of shoring up the decisions that the off-path ideas would take. Maybe hold on to that thought until we come to that example. Okay, so just a quick sort of just is SDN based control just enough. So this is a simple elastic situation, scaling kind of a situation where you have two traffic flows, a red traffic subset and a blue traffic subset. Each of these devices create state for the individual traffic subsets because these are stateful devices. Suppose the volume of traffic on these individual traffic subsets grows, causing the intrusion prevention system to run hot. You decide to deploy another instance, and essentially what you want to do is you want to shed half the load now. So there are two choices with SDN here. The first thing is you can wait for new flows to arrive and punt all those new flows to the new instance. But in this case, there are no new flows, right? In this extreme example, and therefore this bottleneck will persist. So this impacts the responsiveness, liveness property that we were after. Another thing you can do is you can say screw it. I'm just going to move the blue flows. The problem is that the state that was created for the blue flows is missing from its new location, so that impacts the decisions that the intrusion prevention system makes in this case. It may cause it to either raise false alarms or it may cause it to miss detecting attacks. Okay. So essentially what this means is that simple SDN based control is not enough. In this particular case, if you just relied on SDN, then that will make some Milhouse cry somewhere, and that Milhouse could be your network operator or middle box or whatever else, right? Just going back to this picture, what we really need is that in addition to being able to control the routing of traffic, we also need to move the state to the traffic's new location. Okay, so essentially to satisfy those kinds of properties, what we need is something that provides us joint control over forwarding state and network internal state. Okay, so OpenNF is basically a system that addresses this. Yeah, go ahead.
I mean, to justify that, you said you used the extreme example of no new flows.
Yeah.
Is that a valid?
Not really, actually. So new flows will arrive, but existing flows can last long enough that the load never goes down to below the point that you care about. I think it'll be clearer if you think about this as a scaled down situation where you want to decommission a middle box and you want to take load off of it. You just have to wait for traffic to drain out, and it can take several minutes, sometimes even hours for traffic to drain out.
Okay.
Yes, I'll actually show you results where in the simple trace that we analyzed, it took up to half an hour for a middle box
okay.
traffic to drain out.
I'm just making sure that the hill you're preparing to climb is worth the benefit, right? Because you had this sort of straw man for why it is we couldn't use the naive technique of just waiting for stuff to drain.
Yeah, and hopefully at the end of the talk you'll be convinced that that was not a terrible hike of the hill. Okay, so yeah.
Is the state of the art that no state is moved from the old to the new box, or what do people do today when they move from the old to the new box?
So what people do today is the first alternative is to wait for flows to drain out, right? So you want to decommission a middle box, you wait for it to drain out, and then you check it out and start using the new one. So all new flows go to the new middle box, all existing flows have to drain out from the old middle box. There are some research papers out there that just do reallocation. They'll be like, okay, let's just reallocate. But what they ignore is what happens to the false positives and false negatives in the decisions that the middle boxes
I was
make.
wondering if there's like a simple, timeout-based mechanism that I would say, I would wait for whatever X time period, and then after that.
Yeah, the problem is you don't know, right? I mean, you don't know. You're monitoring some state, and you don't know whether you don't know how long you would have to wait.
Right. Yeah. I'm Yeah, this would be an empirical solution again.
Yes, and flow lengths can be arbitrarily long, and you have to wait for that tail flow to finish. Right?
Just to make sure I understand the abstraction right, one is, are you trying to provide a sort of an atomic operation which essentially would say that consider this set of metal boxes as a single logical unit?
Yeah.
Right. So and from an end-to-end perspective, you don't really care whether the flows are traversing a single box or multiple such boxes, as long as we can, I guess, coordinate the coordinate the state from one to the other, I guess. So perhaps, I presume the example goes beyond n equal to 2.
Yeah, from an end-to-end perspective, or the tenant or whoever is using it, he just sees that as one middle box, okay? And there is a control application that wants to preserve that abstraction of that one available middle box that offers a certain kind of performance. And to do that, the control application may need to do some reallocation of processing, and we want to ensure certain semantics for that reallocation of that processing. Does it make sense?
But one other point essentially here is that, particularly IDSs and firewalls are notorious of, falling down under high load.
Mm-hmm.
So when your control application is trying to do this reallocation, it could just be that, you waited, because presuming you would have some notion of a signal smoothing function. You don't want to sort of become aggressive at the very slight impression of an overload. You want to start doing this rebalancing or reallocation because it just could be transient. But at the same time, you're also risking a risk that it's just like a ticking time bomb now. By the time you do any sort of reallocation, you essentially have lost, say, 80% of your traffic just because the box went down.
Yeah, so I think that so in this picture, right? So this is sort of the OpenNF controller. So what you're describing is this application up there, the elastic scaling application. So all of that would be in the logic for the elastic. At what point does the application trigger a scale out? And that's sort of an imperfect science. So the application may decide, once the middle box sees more than 60% load over a 10-minute interval, I'll start to spin up a new instance and start sending load there. So that's a policy that's up to the application, right? And we are not saying one way, we're not advocating one way or the other what that policy should be, but that's up to the application, right? Once the application makes those choices, it would essentially translate that down to some set of reallocation operations, okay? And that becomes some sort of state import and export across these middle boxes. And so the OpenNF controller does those things in coordination with the network to support some semantics for those operations, and those operations will complete safely and within a certain amount of time.
Agreed with all of that. But I'm saying, going back to the slide, a few slides back, where you're talking about both safety and liveness.
Yeah.
Right. So you had an implicit sort of, choice of what essentially says soon enough.
Yeah.
So now that soon seems, explicitly now tied to how sensitive or how aggressive you are in triggering this particular function, right? So you cannot just give any sort of arbitrary guarantee. You're essentially now saying the guarantees are now
So essentially, what we want to do is, what can the controller provide, right? So if the controller can say, look, you give me some kind of reallocation operation, I can give you a done signal within 500 milliseconds. Okay, so that's the kind of soon enough kind of guarantees that we are after. Okay.
After you trigger, then essentially you're saying that there's a bounded amount of
time that it will take to be done, but that is a bounded amount of time. And we can reason about how long that's going to take, and it is going to be small. And I will show you how we get there. Does it make sense?
Again, I guess maybe perhaps I'm jumping in, but depending on the amount of state you have to transfer. Right?
Yes. Yeah. It's all known, and I will tell you why that is the case.
Question?
Yeah.
So do you pause the traffic during the transfer?
No. So again, I'll get to that. No pausing of traffic happens. Traffic is getting processed, and that's the thing that we have to deal with. That's a big problem. It creates problems for us. We don't want to pause the traffic. Yeah.
But so how can you do that if you decide at this point you want to transfer the state, new packets are coming in, they start updating the old state.
Yeah. Okay. So what you're talking about is this race condition. Okay, so I'll get there. That is the biggest challenge in designing OpenNF. Okay, so these are the challenges. So the first thing is we want to be able to bring in arbitrary NFs that are out there into the fold. We don't want to change anything about how they do their internal state reallocation, because that may restrict the set of NFs we support. What you are referring to is this big challenge that we have here. As we are moving state, packets arrive and update state, and so state, those updates may be lost at the state's new location, or they may happen out of order, or state can become inconsistent in some way, and we want to make sure that doesn't happen. And those are the guarantees that this is the safety guarantees that we want to provide. Any other questions before I jump into the technical part?
I think the first guarantee is probably just purely empirical, right?
Yeah, so that's...
In theory, you can have an NF which is not partitionable, movable state because it has a global lock of states. But I'm guessing to say in practice that doesn't happen.
Yeah, so in theory you can have an NF that doesn't fit in this, okay? But what I'm going to talk about is that in practice, what the NFs that we looked at essentially either create state that either applies to a single flow or some group of flows or all flows. So this is Bro's internal state. So there is a per connection object that consists of two objects, a TCP analyzer object and an HTTP analyzer object. There is a bunch of state that is shared across connections. This is like, per host counters, which is often used for scan detection. And then there is a bunch of statistics that are maintained for all traffic traversing the Bro instance. Okay, so we can basically think of state as being defined by these three different scopes. Either it is per flow state, or multi-flow state, or all flow state. And we can use the traditional notion of flow, which is the connection phi tuple, to describe what state we are interested in and where what we want to do with that state. Okay, so the API that speaks directly to the NFs is actually fairly simple. It has three calls: get, put, and delete. The calls would take a filter F that describes the state that we are interested in, which is typically some subset of the connection phi tuple. Don't cares are allowed. It also defines the scope, whether we are interested in the per flow state matching that scope and that filter, or the multi-flow state, or whatever. But the key thing is that once that get, put, or delete call is issued, it is up to the NF to identify and provide all the states, all the state matching that particular filter. And that is for when it is exporting state. And when it is importing state, it is up to the NF to combine the state provided by the controller with its internal data structures. Okay. So what this means is that the controller doesn't need to know what the internal state organization is. We're kind of punting all the work to the NF. And we also don't need to change the NF to conform to a specific allocation strategy. Okay, so this doesn't obviously make it easier to change an NF to bring it into our fold, but at least NFs don't have to be redesigned to work with OpenNF. Okay, so let me actually get into these race conditions and what I mean by these, how they may interfere with the kind of semantics we want to offer for these high-level operations. So first I need to tell you what these high-level operations entail. So suppose here we have two instances of an off-path intrusion detection system, and the high-level operation is to reallocate port 80 flows to this instance, and that's the blue flows. So the first thing you would want to do is to move all the flow-specific per flow state corresponding to the blue flows from NF1 to NF2. Here you just want to do it for port 80 flows. The other thing, and this includes both the TCP analyzer objects and the HTTP analyzer objects that I described on the previous slide. The other thing you may want to do is you may want to copy the state that is shared across flows. Recall those connection counters that were maintained per host. You could have some hosts connections go here and some host connections go here, so you'd need to maintain copies of that state, right? And essentially the high-level semantics we want to offer for that reallocation operation over there boil down to semantics for move, copy, and share, right? So in particular, for move, what we can provide is that the move is loss-free and order-preserving. And for copy and share, it's various notions of consistency, like eventual, strong, strict, whatever. Okay. Okay. So let me describe very quickly the move operation and then the race conditions. The move operation starts by the control application issuing the move. The controller issues a get call. The NF returns a bunch of chunks of state with flow IDs. Each ID is basically some subset of connection phi tuple things that describe what the state corresponds to. At some point, the controller issues a delete and then puts these chunks one at a time into the destination instance for this move. And at some point, it updates the forwarding controller. The race conditions arise because of this import of state and export of state and the interactions with the forwarding. Let's start with the simple race condition, where updates can be lost. And this arises because packets arrive as state is being moved, and that can lead to some bad consequences. So here's an example. Packets arrive, they establish this state. You've issued a move for the blue flows. The blue flow state has moved. At some point, another packet comes in. It updates the state at the old location. Routing has been updated. And the problem here is that the updated state due to B2 is missing from the state's new location. In the case of an IDS instance, for example, if it's looking for signatures or MD5 checksums to check against some kind of an attack, depending on how it is implemented, it may either miss that attack because it computes an MD5 and it doesn't see that signature, or it may throw up an alarm saying, I saw something bizarre. Okay, so both of those things are sort of things we would like to avoid. Okay, so one solution for this is just stop all traffic, stop all processing, buffer all the packets, let the state move, then reallocate flows. Now this can last hundreds of seconds, you may have to buffer a lot, but the more important problem is that when you stop traffic, there may still be some packets that were traversing, and updates due to those packets to the state may be lost, and you have no way of knowing whether those updates were lost or not. So the high level semantics that we want to provide, something we call loss freeness, is we want to make sure that all state updates due to packet processing are reflected in the transferred state, and every packet that a switch receives should be processed by an NF instance. Okay? Those of you who are familiar with the consistent updates paper that does the one-shot update, essentially it provides the latter property, but it cannot provide the former property. So we are interested in a stronger consistent update property than what the Write-Blatt paper kind of offered. Yeah.
I'm also making an assumption here that your NF1 has sufficient capacity to, because it might just be, I mean, you're worried about race condition, but the opposite of it could be true that.
All of that is up to the control application. We are assuming that the control application is monitoring that, and when it tells us to reallocate, there is a reason why it chose to reallocate.
No, that's fine.
Yeah.
What I'm essentially saying is, in terms of when you look at the updates being applied, or like a new flow came up, perhaps it doesn't have sufficient capacity, so just it drops that request for a TCP SYN on the floor. But then, so what is that treated as? During the transition, during the migration, right? The new flow that was supposed to be established, and it sort of goes back to the original condition, that the very fact that you are triggering a reallocation is that there is something running hot.
Mm-hmm.
But by the very fact that that thing is running hot, you're also not able to, say, cope up with the, say, new connection, a new rate of connection that are coming in.
Yeah.
So, what sort of consistency or properties does it give? I mean, those connections are dropped, just they're ignored, or? So, I mean, I'm essentially saying I'm trying to get my head around best effort versus guaranteed here. Because to me, that sounds like a best effort thing. Essentially, for things we were able to keep up, we will transfer them, we'll try to transfer them. But there is no guarantee that all the state will still be maintained in a consistent manner. John is raising his hand.
Yeah, so I'm trying to wrap my head around that question. So,
I mean, I guess one possible answer maybe is, does hot mean 90% and you
Yeah.
get out of here before you burn up, or does hot mean 110% and now you're dropping?
yeah, so I mean, I would think that an elastic scaling style application would probably have conservative thresholds. Like, I'm starting to see over some period of time, it's hitting 80%, and then it would.
Control the load. That's the whole point. That's an external signal to your system. I mean,
Yeah.
no matter, even if you start that reallocation at 10%, at 1%,
Mhm.
the load is an external signal. You don't control that.
Yeah.
So unless you can start dropping things anywhere during that transition, you would still drop things. So what I'm essentially trying to understand is you're not guaranteeing them the state then. You're essentially saying, I had some state of the network flows which were passing through me,
Mhm.
right? Some part of that would get transferred to the new location.
Yeah. So what we are saying is that the state we are transferring will not see losses due to the transfer. Okay, it could see losses due to whatever the middle box is experiencing, right? That's up to the implementation of the middle box. Okay, so our transfer doesn't impose any other losses in addition to that. That's the guarantee.
Then how are we better off than not doing anything at all?
I think the common case is better. I think you were zooming in on corner cases where you cannot predict the load, and the load is so high that some things get dropped and whatnot. But I think maybe the way to think about it, in the common case, where the load is not wildly fluctuating.
Is that the common case?
I would say that is the common case.
It's not.
Why not?
Because things fail. I mean, that's the point.
Things failing is not the common
No,
case.
things failing due to overload. That's the point. So
It's not a common case. Like load moves smoothly in the common case, right? Like because load can be modeled. So it's all boils down to, I think, how conservative the control application wants to be. So the way to look at it, I think there's an opportunity, in some sense, to work in that. So yes, bad things will happen, in which case, like nothing will provide a guarantee.
Right. So that's a question. Right?
Let's take this. Yeah, I think that's this. We should probably take this discussion a little bit offline because I have like half the talk to cover. Yeah.
When you talk about migration, there's also tons of work in VM level migration.
Oh yeah, I'm going to come to that. Okay, it doesn't work for scale down. Think about it, right? How would you use VM migration to scale down?
Well, I was thinking in terms of if you replicate each incoming packet to both instances, right?
I'm talking about scale down. When you want to collapse two instances into one instance, how would you use VM replication for that?
Not replication, migration.
Okay, we'll come to that.
Replication, migration of state.
Okay, well, what do you do? So you have two VM instances. How do you merge their state?
I mean, you essentially will have to apply some NF specific logic to send.
Yeah. Okay, that's complex. So we'll come to that. We'll come to that. I mean, I think we are going off in a very bizarre tangent here. Okay, so the key idea we have is this, something called event abstraction that I'm going to use to address all the race conditions. So this is basically a way of preventing state updates from happening and then sequencing them in a particular way. This also helps us reason about the time it would take for these operations to finish. So the simplest way we do this is packet comes in, we enable this event. It applies to all the blue packets, and what this tells us is when a packet is received, raise an event to the controller, but drop the packet locally, don't process it, okay? So then we issue get and delete, state is moving to the second instance, packet comes in, event gets raised, packet gets buffered at the controller along with the event. Eventually state gets put returns, and then the controller flushes all the buffered packets to the destination instance. Any packet that arrived along in the interim is handled in a similar fashion. At some later point in time, the forwarding is updated, and then all the packets that arrive along the new path are updated similarly. So if there are any remnant packets, they raise events, they get processed, but all the packets get processed, no packet is left behind, but they may get processed out of order. Make sense? So we can prove that this actually ensures the move is loss free. Going back to this out of order stuff, things can be processed at the middle box in an out of order manner. Again, this can happen because of the interactions between the steps 4 and 5 on the previous slide, where we were flushing the buffer and updating the routing. So buffer gets flushed with the events in it, 2 packets get sent to the destination instance. In the meantime, because the routing has still not been updated, an older packet comes in, goes to the older instance on the blue flow. The event gets generated, gets buffered at the controller. Then we kick in a routing update. Suddenly a new packet shows up, gets sent to the new controller, and then the controller eventually releases the buffered packet, and so the packets are processed out of order. This matters for something like Bro. Bro runs this thing called a weird activity script that looks for things like requests happening after a response was seen, or a SYN happening after data was seen. Those are indications of attack, and these can trigger such alarms inside Bro. Okay, so the key order we want to make sure is that all the packets are processed in the order that they were forwarded to the NF instance. Was there a question? Makes sense? Okay. So again, the basic idea we have is we want to keep track of every packet, but we want to know what the last packet seen by the old instance was, and then sequence all updates around that last packet. Okay, so the way we do this is we again flush all the packets just like in the previous case, but we mark them with a do not buffer flag, which means that the destination has to process them. We enable events on this instance, but instead of dropping the packets, we tell the instance to buffer and hold on to any packets that it receives. But instead of just blindly updating routing to send to the other instance, we first create an update where packets are replicated to the controller and to the original instance. And what this tells us is anytime any packet is sent to the controller, an event gets sent to the controller and eventually gets sent to the flushed to the destination where it is processed. But it helps us keep track of what packets, remnant packets, the first instance is seeing. So we will know which one is the last packet that the first instance NF1 saw. So what we do is, suppose B3 was the last packet that was seen by NF1. We have updated the routing state. Some other packet comes in, it hits this event, gets buffered locally. But at some point, this packet gets processed, it will raise an event to the controller. So now we know that the last packet B3 has been processed by NF2. Once that happens, we can release all the buffered packets and let them be processed. So we kind of can sequence the processing of packets by issuing events of the two instances. Yeah?
I missed this if you did, but why bother making sure they're in order? I mean, they could have been out of order anyway. Are you just trying to not introduce?
Yeah, so we are talking about things going out of order in different directions of a connection. If they are within a connection, typically the middle box will do reordering. But if it happens across directions, the middle box has no way to know whether that is weird or whether that is normal. Okay? Ratul, does that address the original question that you had?
Yeah, I think the answer is that middle boxes are sensitive to reordering.
And we want to,
despite the network contract or whatnot.
Yeah,
It seems there's an expectation that normally that doesn't happen, and
Yeah.
if it happens a lot, it's okay to raise a false alert.
Yeah.
Things like that.
Yeah, we don't want to exacerbate that. We don't want, yeah, exactly. It's well put. Yeah, Ganesh.
How beefy are you assuming that controller is in terms of maintaining the way it's like?
Very beefy. Okay, so the controller, right now we have an unoptimized controller. It can handle, I don't know, a few hundreds to thousands of events per second with buffering and all that. We haven't optimized that further, and it also has one socket that it listens to for everything. It's kind of very poorly written right now. But that's an active area of research. How can we make this controller robust and beefy? But we don't see any fundamental bottleneck to scaling that. Okay. Okay, so just quickly about copy and share. Copy is an operation that provides eventual consistency of a state across middle box instances. Share is something we can use to provide stronger version of consistency. It is kind of, it's like a poor man's version of share right now. Essentially what we do is we stop packet processing from all instances that are sharing state. We have them all generate events. We queue the events in a FIFO order and then release them one at a time to NF instances. And once we know that an NF instance has changed the state, and that is known through an event, we then trigger copies of that state across all of them. So it's sort of like very heavyweight implementation of strong consistency. Okay, so what do applications do? They decide on the granularity, they decide on the scope, which state they want to operate on, whether multi-flow or per flow state, and the filter, whether it should be a per prefix or just port 80 flows. And they also decide whether to move or copy or share that state. And they also can describe the guarantees that they desire. We provide 3 for move, no guarantee, or just loss freeness, or loss freeness and order preserving. For copy, it is either no or eventual consistency, and for share it can be various versions of stronger notions of consistency. Okay, so let me describe this quick application and then I will go into the evaluation stuff. The point of this application is to show some of the choices that can be made with respect to the API that we have designed. So this is Bro. I don't know why they chose the logo. It looks like a zit in your eye, but that's what it is, right? So here, typically Bro runs, these are very popular scripts. This is a scanning script that looks for connection counters. This is a vulnerable browser detection script that essentially looks for all HTTP requests and analyzes the signatures. This is that weird activity script that I was describing that looks for both directions for bizarre stuff to happen. Okay, so here are 2 sets of flows and the third set going through the third middle box, and what we want to do is we want to move some prefix between 2 middle boxes. This is the prefix we want to move. This is the old instance, and that is the new instance we want to move to. The first thing that would translate to is basically copying state from all the multi-flow state from the old instance to the new instance. So this is the multi-flow state connection counters we want to copy. That's important for the scan detection stuff. And we want to move the per flow state from the first middle box to the second middle box. This describes that it is per flow, and these are the guarantees we want. We want loss free and order preserving, and I'll get to that in a minute why we want those strong semantics. And the way we do sort of eventual consistency is we have a loop that every 60 seconds copies state across those two instances, copies the connection counters from A to B and B to A. Okay. This is sort of what this application would look like, the way it is written. So the key thing to notice is that this multi-flow state is needed for the scan.bro script. The vulnerability detection stuff, that's mainly looking for poorly designed browsers, needs just loss freeness. It doesn't need loss free and auto preserving because it's only examining one direction. But weird activity script needs both guarantees. And again, this recopying is necessary for the scan.bro stuff. So you probably would have to look at your application, and then based on that application you can decide what kind of guarantees you want and what specific chunks of flow state you want those guarantees to apply to. Does that make sense? Okay. I had a more complex example of an application, but I won't go into that. I want to quickly go over results and just talk about whether we can deliver on the promise that we had earlier. But are there any questions at this point? Is this kind of clear how the application would get written? Okay. Okay, so this is a real thing. We have this controller that we wrote on top of Floodlight. People are familiar with Floodlight. It's a Java-based OpenFlow controller. So it's written as a module in Floodlight. We provide a shared NF library, roughly 3,000 lines of code. And we modified a bunch of different middle boxes out there. Bro, an intrusion detection system. This is an asset detection system, which looks for various signatures of different kinds of operating systems running in the network. A firewall and NAT, and a caching proxy. Roughly up to 8% increase in lines of code. For Bro, which was the most complex thing we changed, this translated to something like 600 to 700 lines of code we had to add to support OpenNF. Okay, so just some quick micro benchmarks. What does this mean for the kind of actions we need to have the NF support, and what does that mean for the high-level applications? So this basically shows the performance of get and put per flow across three middle boxes that we modified. And here what we are doing is we have some number of flows whose state we want to get and then put, and we vary that number, and this is the total time it took to do that operation. So the big point to notice is that first get per flow takes a lot of time, lot more time than put per flow. And we sort of if you look at the 1,000 flows case, in the case of Bro, for example, get can take up to 850 milliseconds. And the big contributor to this cost is the serialization and deserialization of state in both cases, unpacking state, changing it into a wire format, and so on. The other thing to notice is that as the complexity of middle box grows, the complexity of the state also grows. But the key point is that once you have a middle box, you can benchmark these things and you can kind of know how long it would take for a certain sized state to be read or written. Okay, what does this mean for the operations? What kind of guarantees can we provide that some operation will complete in a certain amount of time? So here the setup is we have 5,000 flows in some middle box, and we want to move all the flows with their per flow state. The middle box is seeing about 1,000 packets per second, and it is 50% utilized. If we have no guarantees requested, the move operation finishes in about 250 milliseconds. This is actually almost exactly the serialization plus deserialization cost. We can parallelize it. In this case, what's happening is first all the flow state is being read and then it is being written, but we can parallelize read and write, and that will improve the overall latency further. But the point is that in both of these cases, there are packets that are dropped as state is being moved. That's up to 200 packets. If you kind of see, that's the number of packets that get transmitted at 1,000 packets per second for the 250 milliseconds it takes to move the state. So suppose if we do loss free with the same parallelization optimization, we see a slight increase in latency due to handling of events, right? And that translates to, on a per packet basis, an average latency increase of between of 100 milliseconds and a maximum latency increase of 250 milliseconds. This is because buffered packets will have to wait for the state to be transferred, and then buffered packets get released. And this latency is exactly the total time it took to put the state. And there are about 230 packets in events. Again, this you can calculate. because you know again the load that the middle box is seeing, and you know how long it would take for you to move the state. With a different optimization, we can bring down the per packet latency even lower, and essentially what this optimization says is, in this case, we wait for the entire put for the whole state to return, and then we start releasing events. But we can wait for individual chunks of state to return and start releasing events corresponding to those chunks, so we can reduce the amount of time packets are buffered at the controller. And if you want the stronger guarantee, you end up seeing higher latencies, and a lot of the higher latency here is because of packets buffered at the destination instance waiting to be processed. But the key claim though is that these latencies, on average latency seen by a packet or the total completion time, can be calculated, making some assumptions about the network. It's a function of the load, the 1,000 packets per second, the amount of state that you're moving, which is a function of how many chunks of flows you have seen so far, and the processing speed of the middle box. Once you know these things, you can kind of predict that I will finish this safe move operation within a certain amount of time. Okay, and that we argue is something that can form the basis for SLAs. Yeah.
Can you give us some intuition of what that function looks like? So I'm curious now, like realistic workloads I would add, say, at least 2 to 3 zeros in your so what would the latency numbers look like? Workload becomes 100,000 PPS to 1 million PPS.
A single software instance? I doubt it.
Absolutely, yes.
A single stateful software VM.
Yes.
Million packets per second.
Yes. Oh, I wouldn't say like it could be an extra large VM, say, but like a standard 8-core box. Yeah. I mean, this is on the lower end of things.
Okay, I mean, yeah, sure. I didn't mean to poke fun at you, but that's probably possible.
Yeah, that's different with academia.
I don't. No, it's not a difference between academia or whatever. I was just curious where that was coming from. But what I'm wondering is, why would anything change here?
No. My question is, what would the latency numbers look like? What does that function look like?
Okay, good question. So if you had a million flows, so let's go back to the previous.
Not a million flows, a million PPS.
Sure. I mean, but the latency is determined by how much state you're transferring, and that is a function of the number of flows that you're moving, and the complexity kind of grows. Here. With the number of flows that you're moving, right? So you can kind of imagine that when you have a lot of, it depends on how many flows there are. Even if it's a million packets per second, if it's across 1,000 flows, the amount of time you would take to do the move operation is purely a function of that. Okay, what would happen is when you're moving that state, the million packets per second determines how many events are raised, okay, and how many packets get sent to the controller. That is what the million packets per second would determine. And we need a robust controller to handle that. And we just, it's up to the controller to be able to handle that kind of a load. It doesn't change the time it takes to finish the move operation. If the middle box can really handle that many packets, really all we are talking about is all those packets coming to the controller, and then the controller sends them to the destination middle box and they get processed there. If the controller can handle that kind of a load, we are fine. But the total latency of the move operation itself is a function of the amount of state moved. It has nothing to do with the load.
Well, state, there is some correlation between.
But it depends on the number of flows and how the middle box is organizing.
So, yes. So, if the number of flows becomes 10 times large, is it a linear function, should I expect?
Okay, so well, that's kind of the point of this graph. I think it's kind of linear. I mean, we are doubling the number of flows, and the size of these bars is kind of doubling.
The fact is a little bit more than fluently, at least I'm just eyeballing the graph.
Sure, yeah, but we haven't done fine benchmarking of that, of how the size of the state would grow. But I don't see why it would be anything but linear. I mean, the amount of state for per flow state should grow with the number of flows. Right. Okay, so let me talk about the last thing which kind of got brought up, which is why not use VM replication. Here we did this elastic scale up, scale down stuff again. I'm running a little over. This is probably my last slide. And again, some way midway through, we scale up to a new middle box, and then at some point we scale back down. With OpenNF, it takes about a quarter of a second to finish the scale up and quarter of a second to finish the scale back down. With VM replication, when we did the scale up, we actually found a bunch of bizarre log entries at the scaled up thing. And that, I mean, our best hypothesis is that because of superfluous state that that particular VM instance did not need. And there's no clear way for it to support scale down. Okay? And if you just did forwarding control alone, scale down is delayed by more than 1500 seconds. This was going back to the argument that the question you had, John, how long would we have to wait? There was a particular flow that we saw in our traces that lasted for up to half an hour. And we had to wait for that flow to clear up. Okay? So that's basically it. You know what OpenNF is. It enables fairly rich control over state and distributed processing, and we can provide sort of clean semantics and reason about performance. And you can go to this website to download code and play with it. I don't know if I have time, but I wanted to reflect on the relationship with SDN if I have time, but if people don't, feel free to leave. Do I have a minute?
Sure, you have a minute.
Okay. So Ratul, in the email that he sent out, said this was a talk that was sort of like SDN for middle boxes. So it is and it is not. So SDN provides control over forwarding state. We provide control over NF internal state. So in that sense, it is similar. But in many senses, it is different from SDN. So in SDN, a controller can create state. It sort of computes the outcome of some routing protocol and creates a forwarding state and pushes that forwarding state. In OpenNF, we made a conscious choice not to do that. We are just handling state. We are moving state or we are copying state, but all the state is created by the middle boxes. We haven't ripped that logic out and re-implemented that at the control plane. That was a conscious choice because we couldn't figure out a common way to do that across all the middle boxes. The purest view of SDN is that network elements are dumb, control plane is ripped out and implemented somewhere. OpenNF is not so pure. There is still a lot of stuff going on inside the middle boxes. We don't really know what ripping out a control plane would mean for a middle box. So in that sense, it's sort of similar to sort of the pragmatic view of SDN. There is still control plane outside in the middle boxes. You have a logically central controller that allows you to play with forwarding state. The other thing with SDN research is that people were like, there was a lot of hype and buzz about SDN, and then they realized, shit, we have to deal with consistency of updates of state. So it came as an afterthought. Ratul has done a phenomenal work in reasoning about various consistency semantics. You can kind of think of OpenNF as sort of SDN with, okay, let's deal with the consistency problem from the ground up. Okay, so that's the relationship with SDN research. Okay, so I'm done. If you have any more questions, I'm happy to talk about them. Thanks.
I wanted to
Yeah.
quibble with this one. Actually, I think the distinction is actually less than, say, like in the end, I think even in the forwarding case, routers, if nothing else, are generating and updating state. If nothing else, open flow counters is an example of a state, and your controllers, well, some controllers make decisions based on open flow counters. In that sense, I think the only difference is, like, yes, you're not moving state or whatnot, but these switches are in the end generating some state based on which decisions get made and things like that happen. So
yeah, I mean, I think you are probably quibbling more with this argument than with this. It's not that the
even the second one, like
but what the point that I was trying to make here is that the forwarding state that gets installed at a switch could be completely determined by the controller, right? A switch starts with something and the controller can say, throw that out, use this instead, right? Mm-hmm. We are not quite doing that. We are letting the logic pertaining to an NF determine what that state should be. All we are deciding is where to locate that state. We are not actually computing that state for the NF.
I think if you look at state, right, like if take proactive SDN instances, right? They are creating state for the switch, and so are you in the sense, like when you create tunnels and things like that, you are proactively telling the switch, hey, here's your state, and do things based on this state.
Yeah.
And in that sense, you're doing the same. I think the key difference is, I would have put it differently, which is like, in a traditional sense, like the SDN controller exactly knows what the switch is going to do. What you're saying is you don't know what this box does, and
Good point.
that's basically it. So a lot of the reasoning that comes from that, right? Like, because you don't know what that state is, you don't know what processing is happening, so you have to be extra careful versus like knowing, hey, this is a forwarding switch. All it does, if I give it state S, this is how its behavior will change. But you don't know that in your setting.
I would say the arguments are kind of related. You know what the switch is doing, and that kind of you can use that as the input to do future computations. Because we don't know what the NF is doing, we cannot do anything about what the NF's processing is. We can only deal with management of that state.
Okay. Nothing else? Okay.
Okay, cool.
Great.
Thanks, Larry.
Thank you.